Good morning, good afternoon to everyone. We hope you enjoyed the health check security video that we ran. Don't worry, you are not in a security session. You are in a microservices deployment session. And today I'm happy to announce that we are joined by Tim Graves, who is your speaker and your let's say guided tour for this demo. Speaking about our speakers and panelists, here is Tim Graves, Marius Popa, and Mika Rinne. They are coming from either the cloud native specialist or the application development specialist team within Oracle EMEA. And I'm going to let Tim actually to speak about himself shortly. Before I invite him to take over the presentation, I would only like to share two things. So everything you see in this call has an educational scope. And if you like to use our services further, feel free to connect with somebody from the Oracle account team. Also, if you watch any of our sessions recordings in the future, bear in mind that there might be some differences in the Cloud Console menu because our products are enhanced on a regular basis. That was all on my side. Tim, over to you.
Right. Thank you very much, Violetta. Right, let me just set up my desktop. Okay, hopefully you can see my slides.
We do.
Excellent. Right. Well, good morning, everybody, and welcome to this cloud coaching session. My name's Tim Graves. I'm a cloud native specialist in Oracle, and along with Marius and Mika, who are helping support this session with the Q&A, and the rest of our team, we work on cloud native projects across all of Europe, Middle East, and Africa. So, let me just confirm you can see the slides, not the other desktop.
We're looking at Tim's Graves Cloud Native
Brilliant.
Specialist.
Okay, excellent. Yep. Right. There's too many screens here. It's easy to get mixed up. So, as I say, my name's Tim Graves. I am, when I'm not working with computers, I'm a keen skier, although have a bad taste in ski clothing. Love cooking, though not professionally, and I've been told I bear a passing resemblance to Santa. That's not a full-time job or anything that I do for a living, however. But it's amazing when you go through the supermarkets and they go, "Hello, Santa," from the little children. So what are we going to talk about today? Well, what we're going to be talking about today is how to deploy microservices in Kubernetes. This is a demonstration and a presentation, but it's based on an online lab that we do. So if you would like to do the lab yourself, there are links and details on the screen now. If you have registered for this session, you can get a 30-day trial, I believe it is. And Tom, I think, is going to be putting some details for that into this event. And you can run the lab in this event. We're going to be covering a lot more in the lab than we do in this demo for time reasons, but we can do that. And obviously, if you have any questions, please shout. There is a follow-up event, which Violetta will be providing the details on Friday at, what time is it Friday? It is, my mind's gone blank. Sorry. It is
2 p.m.
at 2 p.m. CET. So if you've got any questions, you can also join those sessions then. So let's get on with the actual demonstration and presentation. First of all, not everybody on this call is going to be fully familiar with Kubernetes. So what I'm going to do is I am going to give you some basic introductions to Kubernetes to start with before we go into the demo. So first of all, Kubernetes, like many things in the cloud native world, is based on the idea of containers, which themselves are built from images. So an image is basically a way of packaging code. It could be shell scripts, it could be an executable program. It's very lightweight, they're standalone, they're actually built out of a set of layers. So, you know, if you've got the base layer, you don't need to repull that and transfer that again. And they're easy to transport. So things like Docker Hub, any container registry that is compliant with Docker, the V2 protocols and so on. So this is a very simple way to package up your applications in an installed runnable configuration. And that's an key part. This is a runnable thing. It's not like a software package that you then have to install yourself. You just get the container and run it. Now, an image, of course, has to be run. And when it's running, it's run as what's called a container. And a container is a virtualization runtime. There's been a long history of virtualization in terms of virtual machines, but also virtualization within the operating system. And the key thing with containers is they are very, very lightweight. And that is because they run on the same kernel. In fact, from a resource perspective, a container takes no more resources than running the program natively. Okay. It is, however, very secure. Linux kernel has very strong separation between containers, and from a user perspective, it just looks like a very small computer that generally does one thing. Now, a microservice is effectively a small set of services or a small service, but is focused on just doing one thing. So if you think of a storefront, traditionally you may have had a huge application to run your storefront. A microservice is focused on the one specific business function there, for example, a shopping cart or credit card validation or something like that. And these are what's called loosely coupled. In other words, they have a defined interface that we talk to, but one microservice doesn't know the details of the other microservice. Now, microservices are designed, or the concept is designed to be very, very easily horizontally scalable. And this is really, really important as to how we address changes in load in the cloud native environment. A microservice, you can have 5 of them, and then if the load goes up, you can very quickly add a couple more. And because these things run in containers, it's usually within less than a second that you can get the container up and running. Now, obviously, that will depend on what's happening in your application, but because they're small applications, it means that you can generally get them started up quicker. And frameworks like Kubernetes are designed to help you handle that automatically. Now, the communication between the microservices, as I say, is done based on an external API. This is accessed over the network. And generally, it's not required, but generally people use a REST-based microservice with typically a JSON or possibly an XML payload, but you can use other protocols, for example, gRPC. If you are going to be developing microservices yourself, they're designed to use very agile-based processes for our customers out there who update microservices 10, 15 times a day. So they need a very fast development environment, and obviously there's a whole bunch of tooling that you can also get access to help you with that. And as a general comment, if you are looking at building a microservice, if you haven't already, I would recommend that you go and look at 12factor.net, because that'll give you some really good guidelines on the approach you should take to build successful microservices. Now, let's move away from microservices and talk about Kubernetes as a framework for running those microservices. Now, Kubernetes is a stack of elements. There is generally an image registry. This is usually a Docker compliant registry. You could use Docker Hub, for example, if you wanted to, although that does tend to throttle your download speeds. But most people would run a local image registry. And in fact, within Oracle Cloud, we have an image registry service that you can use. The Kubernetes cluster itself is basically 3 layers. There is the control plane. This is what actually runs the cluster. And in the case of a managed Kubernetes service, which is what Oracle offer, that is something that we will run for you. We will patch it, we will manage it and maintain it. There are then node pools, which is effectively the definition of what a worker looks like, and multiple workers, and then the workers which actually run the processing. Now, node pools can be an actual node pool or they can be a virtual node pool. And the workers can be a physical worker, a virtual machine, or it can be what we call a serverless Kubernetes. And that's one worker that only runs one set of processing. And these are usually set up using scripting, for example, Terraform or Ansible. And you'll hear me talk about scripting a lot. I can strongly recommend that you do look to use scripting for creating anything within the cloud, because it means that it is reproducible and automated and therefore reduces error. But you can, if you want to, use command lines or user interfaces for creating your Kubernetes cluster yourself as well. Now, Kubernetes provides a container management framework. This allows you to do a whole bunch of services. Now, the core ones I've put here. There's a lot of other features that come with Kubernetes as well. Now, it provides you with an environment that you can deploy your applications in, all of those microservices. It provides you mechanisms to access and attach storage to those microservices and to share that information. It provides you with a mechanism to access the services delivered by those microservices and also to load balance across all of the instances of those microservices. There are mechanisms within Kubernetes to do rollout and rollback of new versions of software. Rollback is equally important because rollout and rollback is how you deliver these services whilst continuously whilst doing upgrades, for example. We provide mechanisms for self-healing of services. So for example, if something fails, it can be restarted, and also mechanisms for handling the configuration so that you can pass configuration information into your microservices. Very important, you don't put that inside the images. You separate the configuration out from the logic. Now, Kubernetes itself is also in part implemented using microservices. There are a number of microservices that are built into Kubernetes. For example, the Kubernetes DNS service, and you can see some of the other ones that are listed here. Now, let's start talking about how this process works. So what we're going to be doing today is we're going to be looking at a demo, and I've already created a little bit of environment. It takes about 12 to 15 minutes to create a Kubernetes cluster within the Oracle environment. That's very fast if you ever tried installing Kubernetes manually, but that's obviously not something we want to do as part of a demo. So we've pre-created some container images and the Kubernetes cluster. And I've used Helm, which is the equivalent of a package manager for Kubernetes. You can kind of think of it as like Yum or apt. And I've installed an ingress controller, in this case based on the open source Nginx web proxy, and that came with a load balancer. And I've also installed the Kubernetes dashboard and the metrics server. These are things that you would quite often install within a Kubernetes environment. I just install them, as I say, to speed things up. If you decide to do the lab, it will take you through all of the steps of setting these up. Now, let's first of all talk about the flow of getting a request into Kubernetes, because you generally don't use Kubernetes completely standalone by itself. Typically, you have a request that comes in from the internet, and it goes through a number of stages before it gets to the actual microservices. So, in a production environment, a request comes in. I'm just showing a very small piece of JSON payload here. And that would usually, in the case of OCI, go into an API gateway. And that validates things like, for example, ensuring that you've got the right security headers, that you're doing rate limiting and stuff like that. So it's the first level of protection. Then you would usually go through a web application firewall. And this is doing things like protecting against SQL injection attacks. Now, you may have heard me mention a few times that you have multiple instances of a microservice. So you have to use a load balancer to spread the requests across all of the workers, and that is then handed to the ingress controller that will distribute those requests to the services that are running inside the Kubernetes cluster. Now, for the purposes of this demo, we're not actually going to be showing you the API gateway and the web application firewall. We're just going to be taking in a request and effectively doing the network load, the load balancer, and the distribution within the Kubernetes environment. So let's start. We're going to actually do a little bit of hands-on work here. And what we're going to do to start with is we're going to set up what we call the core elements for Kubernetes, if you like. And in this case, what we're going to do is we're going to look at how to set up the namespace, which is, you can kind of think of a namespace as a directory, okay? Then we're going to talk about services and ingress rules. So first of all, let's go to our environment. So this is the OCI Cloud Shell. Just to show you, I have a Kubernetes cluster here. This Kubernetes cluster, it's a very small, very basic cluster. It has one node pool, which is a collection of workers. And in this case, we have 3 workers in our node pool. Okay, so these are all very small workers. In a production environment, you potentially have tens, hundreds, possibly even thousands of workers spread across multiple node pools sometimes. So, you want the managed service to handle all of that. Excuse me. Now, what I'm going to be doing is I'm going to be using some pre-built scripts and environments here. Okay, so first of all, I need to create a namespace. Now, a namespace is somewhere that you can work in. You can kind of think of it as like a directory in a file system, but for elements within Kubernetes. It's also a admittedly quite basic security system within Kubernetes, so that you can separate what one set of processes, applications running in a workspace can see from applications running in a different workspace. Now, Kubernetes has a number of security processes and procedures. I'm not going to go into those in detail, but you do have role-based access control in Kubernetes, so you can give administrative rights to individual users based on that namespace. So If we look here, we have the Kubernetes dashboard. Now I'm just going to log into the dashboard here. Okay. Right, the Kubernetes dashboard has some namespaces. There are a number of namespaces that are built as standard. So, for example, the public system, kube public kube system, and the default. We've also got a namespace that I created for the ingress controller. So we're going to create a namespace. Now, I am going to be using a script to do this. Now, what this script will do is it will create the namespace, and it will also set it as the default namespace that we're going to use when we issue commands. Now, again, I strongly recommend that you use scripts here. Okay, there are other ways of doing control within Kubernetes. You can use things like CICD tooling that will recognize changes in a Git repository and automatically apply things for you. But I would recommend, except possibly in a development cluster, that you don't do stuff manually, right? You want to automate this as quickly as possible. You want to protect yourself against errors and bugs and stuff like that. So that's now created a namespace. So let me just zoom in on this dashboard, and you can see that we now have a namespace called TG. And if we go into it, we can see a little bit of information. But if we look at that namespace, let's go back in here. There's nothing running in it. We haven't done anything yet. We've just created an empty namespace. So the next thing we're going to do is we are going to create services. Now, you can kind of think of a service as like a DNS address, okay? Kubernetes runs an internal DNS mechanism, and actually your applications talk based on that DNS thing. So if we have a look at the one of the services we're going to create here, this is a Kubernetes manifest file for the service. Manifest files are written in YAML. I personally hate YAML, but that's what they've chosen to do. But anything that's white space sensitive really scares me. It's so easy to make a mistake, but this is Kubernetes. And in this case, you can see here the YAML configuration, and we're just defining a few things. We're defining the type, in this case, cluster IP, which means it's only going to be accessible from inside the cluster. We're giving it a selector, which is saying this is how you map it onto the deployment or the implementation. And then we're saying here are some ports that I want to listen on. Effectively, this is going to set up a DNS entry for us. So again, there is a script. I'll show you what that script looks like in a second. Now, this script deletes any existing ones and then creates some new services. And we're having 3 services created here. Zipkin, which is a tracing engine. That will let us see the request flow across a flow of requests across the multiple microservices. The stock manager, which interacts with an Oracle database. In this case, there's an autonomous database. And the storefront, which is what does the business logic. Now, the command to do that script is pretty simple. As you can see, it basically does a whole bunch of commands, and it uses something called kubectl. Kubectl is, if you like, the control program that you use to interact with Kubernetes. It's a very powerful tool. It can do an awful lot of things. But in this case, we're just telling it we want to apply a configuration file, which is the configuration files we looked at a moment ago. So now, having created our services, we can see what those are. So if I get our services running the kubectl command, we can see what they are. If a service was an external facing service, it would give us, for example, the load balancer information. I do apologize there. Now, one thing you don't want to do is you don't want to have a load balancer for each service. And this is where the ingress controller comes in. So the ingress controller is sitting in ingress namespace, set that up earlier. And here it does have an external IP address. And that's because we talk to the ingress controller, which acts as a proxy to then send the requests to those elements. Now, when you're running on the public internet, you generally want this to be secure. So you have a certificate. Now here I am just using a little program called Step. It's a very simple program, but lets me easily and quickly create certificates. In a production environment, obviously you would have real environments. Oops, sorry, and I've just realized I need to copy and paste another command here. Hang a second. So I'm just going to set an environment variable here that is the IP address of my external load balancer. Oops, sorry. Now, I am using a domain name system called nip.io. This is a very simple domain name system in that it looks in the domain name for an IP address and then it returns it as if it was the IP address for the domain name. So effectively, what we're doing here is we are adding we're creating certificates and we're embedding the DNS name into the certificate, in this case, because it's got the IP address, that's what we're doing it. The reason we're doing it this way is because we are protecting against inbound requests being intercepted or modified or whatever. In a production environment, of course, you would have proper DNS and you would have a proper certificate authority that comes into play. So what I can do now is I can create a Kubernetes secret. Now, a Kubernetes secret, we're going to look at those in a little bit more detail later, but a Kubernetes secret basically, in this case, is packaging up that certificate in a manner that can be accessed by services. In this case, the ingress controller that we just created. I'll talk in a bit more detail about certificates in a moment. Now, lastly, what we're going to do is we are going to deploy our ingress rules. Now, let me just start that up. Okay. So it's basically just applying that set of configuration. So if we have a look at an ingress rule here, an ingress rule basically defines a couple of things. It specifies the host to listen for and the security secret that contains the certificate for those hosts. So in this case, if you have that host, you use the certificate in this location. Of course, this does mean you can have multiple certificates running in the same host if you've got multiple DNS entries pointing to the same IP address. And this is something that is quite often done. It then says anything that comes in on this host with a path that begins /store, in other words, it's prefix /store, send it to the storefront service, and we're using the port name that we did when we defined the service. On the other hand, if it is exactly /openAPI, we also pass it to the storefront service. But we can do some more clever things here. We can do, for example, something like regular expressions. So what I'm doing here is I'm defining a regular expression saying, or an ingress rule saying basically pass the second part of a regular expression to the backend service. Again, I specify the security key, and here I specify the regular expression that says anything beginning /sf followed by stuff is what gets passed to the backend service. Now, there's a lot of options here. I'm not going to go through all of them. This is just an example to show you what's happened. Now, what we have just done here is we have just created a service, and that we have created an ingress rule attached to that service. What that means is that we can now try and send a request to the ingress controller, and it will try and look for that service. So let's just do that. So I'm going to make a request to the store service. 503, not available. That's because we haven't done a deployment at the moment. If I change this to some random text, of course, I get a 404 because we haven't set up an ingress rule for that. So what we've done there is we have set up some of the core elements for routing the request to the backend service. So, oops, let me just get through that again. I'm sorry, I thought I'd already gone through that slide. My apologies. The joys of jumping between presentations and demo screens. So, the next thing we have to do is configuration. Now, you don't want to embed configuration into your container because that's a really, really good way of, for example, giving away a database password. So what you do in Kubernetes is you separate the configuration from the container. You do not embed it in images, especially if you want to use the same image for multiple applications with different backends perhaps, or equally, you're going to be changing it regularly. You don't want to rebuild the container every time you do it, in addition to obviously all of the security environments. So with Kubernetes, we support something called config maps and secrets. They're basically the same thing. A secret is just a more secure storage around this. So for example, secrets can be stored in the OCR vault. And these both contain a set of key values. The key is obviously the name, the value is the contents of the secret. And these can be brought into your container in multiple ways. It can be brought in, for example, as a volume or a file system, in which case the key is the name and the value is the contents of a file. So for example, for a database wallet, which is comprised of a lot of files, that's one thing you may want to do there. But equally, it could be brought in terms of an environment variable. Quite often, for example, for programs that use JDBC, they use environment variables to define things like the password for the database. And we'll see in a moment how you can pass both of those in. So let's go and look at how this works. Now, I'm again going to use a script here. Now, just to be clear here, this is not something that you have to do. You can obviously do it by hand, but I'm going to run it as a script, and I'll just quickly show you what the contents of that script once this is finished. So again, my scripts generally do a bit of tidying up to make sure that we're in a known state before then start deploying things. That's the way I do it. You, of course, have different options. So if we have a look at that script, again, it's using kubectl to delete things. And then if we look at this, for example, in this case, we are creating a secret from a file. What that means is that it will create the secret using the file name as the key and the file contents as the value. But we don't have to do it like that. We can create a secret using a configuration map where we define the key values directly. So if we go to the dashboard now and we have a look at our secrets, we're going to see the secrets we just created. So for example, the stock manager database secret here, data source class name is the key, the value is the string. Okay, and if you're curious, we can see that this is actually set up effectively using YAML to set up some name value pairs. Okay, so that's how we create secrets. Configurations is basically the same thing. It's just it's not as secure in terms of storage when it gets onto the disk. And again, I'm going to use a little script to set that up. Oh, one thing, when you display a secret, it usually comes up in base 64 encoding. Okay, I know that's not very secure, but it helps against a little bit of looking into it, right? Secrets can be stored in vaults. You can obviously put security around secrets and stuff like that. So again, I'm going to create some config maps here. We're going to have a quick look at one of those config maps. So if we go here, here is my config map for the storefront. It's defining a store name, some properties, where the tracing service is, where to send the metrics data, where to send the health data, and things like that. This is just a standard config. Okay. If we looked at the secret for the database wallet, however, you will see that these names are basically the names that you find in a database wallet if you've downloaded the database wallet ever. And if we then look at, let's say, the TNS names file, this is the contents of the TNS names file. So what we have done now, we have created our configuration. Let's talk about deployment, and then we're going to go and actually set these up. Now, we have the elements we need. We've got the ability to send a request to our service. We've got the ability to do configuration for our service. What we're going to do now is actually deploy the service. And a deployment describes the overall implementation. So you've got a storefront deployment, a stock manager deployment, a Zipkin deployment in the case of what we're doing here. Now, within the deployment, there are replica sets. Now, replica sets do a couple of things. They manage particular configuration versions. So every time you change the configuration, you're going to, or the application code, you normally change the container image tag and therefore the configuration, you get a new replica set. But it also can handle things like how many instances you've got. So you say in the replica set, I want 20 of these. If it fails, one of those, it'll start a new one to make sure you've got whatever that number is. And then you have pods. Now, there are multiple pods. Usually within a pod, you have one container, but you can have multiple containers. And the pod is what is the actual bit of thing that does the work that implements that particular version. For the sake of ease of use, we generally define all three of these in the same file. We'll have a look at that file in a moment. And Kubernetes will automatically maintain the version. So if you update the file, if you make a change, Kubernetes will keep track of that for you. So therefore, you can tell Kubernetes to roll back without having to specify what that looked like. Really useful if you make a mistake in your configuration file and it's not under configuration management. So let's have a look at how we do that. So again, if we go back to our workload, we've got nothing in our workspace in terms of workloads. So I'm just going to deploy that. Okay. What this is going to do is it is going to create 3 deployments. Now, what it actually does, if we look at the YAML file, which we'll do in a second, it just goes and deploys basically 3 files. Okay. We've now got a dump of information. You can see there's bits and pieces here. So this is telling us everything that's happening around how this workload works. We've already seen how the service works, but then you can see that we have deployments, we have replica sets for those. Now, in this case, we've only got 3 replica sets because this is the first time we've deployed it. If we've made a change and redeployed it, then we potentially would have a different replica set where those changes have been made. And then we have the pods. Now, you can see it says ready, 1 of 1, and things like that. Within a pod, we can have multiple containers, and this is telling us that we've got 1 container out of the 1 container running. Okay, running means it's up and operational. Container creating, on the other hand, means that we're in the process of starting this. So, this output came along almost immediately that the script was run, so we wouldn't get that. If we do kubectl get all now, we should see that all of our services are in the running state. Okay. Now, the replica is telling us that we've asked for 1, we have 1, and that is ready. In other words, it can respond to requests. And I'll talk a little bit about what that means in a minute. And then the deployment is basically saying that, yep, you're there, it's running, it's deployed. Now, let's have a quick look. First of all, the script. So the script literally just applies configuration files. So let's have a look at our storefront configuration file. And this is effectively the deployment. So it specifies the deployment, then it specifies the contents of a replica set. Now you're going to see this labels and match labels a lot. This is how Kubernetes knows how to connect the various elements together. So you have a match label that says this is what I'm looking for, and then you have a label in your metadata that says this is what I am. There's a lot of flexibility here. You can also do things like have multiple sets of labels, so you could match on some but not all, for example, for testing operational applications in the real environment, but only sending certain requests to certain applications. This bit here is about how we handle metrics and processing, and one of the things that we're planning on doing is offering another follow-up to this where we talk about how you do things like metrics processing and so on. And then we have our container definition. So this is effectively the template for the pods. There's only 1 pod in this case, but there could be multiple. We specify where the image is coming from. We specify that in this case, we always want to pull that image because we want to make sure we get updates. We specify some network ports. This is equivalent to specifying ports in Docker, if you've used the Docker port specify command. Some resources, so we can specify a limit, as in it will not go beyond, but also a requirement. So we can specify a guaranteed minimum, and this is how we handle our resource management. The next section of a file is to do with health and readiness. So Kubernetes can automatically restart things. It can track for things being available. We'll talk a little bit more about how that works in a minute. And then the last section of a file is defining volumes. So the first bit is the volume mount. So it's saying this volume gets mounted to this point in our container. And we'll go and have a look at that in a minute. We also specify a little bit further down where the volume comes from. So in this case, conf_secure comes from a secret named conf_secure. Now I mentioned before about injecting environment variables. So let's have a look at how we can inject an environment variable. Oops. So in this case, very similar concept, but you can see that I have an environment section here. So I am injecting an environment variable which will be set up as the container is started. So I have an environment, JavaX, data source, whatever. For those of you who've ever programmed using Java database libraries, you'll know that that tells it where the database class comes from. And I'm saying get the value from the secret, stock manager DB, and the key within it, which is called data source class name. So that automatically gets injected. Let's have a very quick look in the dashboard. So if we now look in the dashboard, you can see we've got our deployments and so on. Let's have a look at the storefront pod. I can see in the dashboard my logs. There's the log information. And Kubernetes is really helpful. If I want to, I can even effectively SSH into these pods. So if we have a look here, and we have a look at the configuration directory, oh no, this is a very small container, so I haven't got all of the commands in here. You can see that it's got the configuration information, but we had, when we had a look at that configuration file earlier, or that configuration information. And we'll see in a minute how we can change that. Now, let's just show you that this is actually there and working. So we're going to make a request to our microservice. And what we're going to do here is we're just going to go and ask it to get some basic information for us. So let me just get a command that will go and pull that information out. Right, here we go. So let's make a request to our microservice. Now, this is going to take a few seconds to start with. This is because the framework I am using inside my containers is what's called lazy instantiation. So although the program is running, it doesn't actually set everything up until you make the first request. That would have taken about 10 seconds. You're going, well, that's quite a long time. And yeah, it is quite a long time. But what we can do is we can actually look at the tracing engine here. So let's go and have a quick look at this. I am just going to go and open up, where's it gone? So let me open a new tab here, and just copy this one to start with. It's easier to do that. So we're accessing the storefront, and we're going to go to the Zipkin service. Okay, so Zipkin is the tracing engine. We're getting a certificate error. As I mentioned before, we're using self-signed certificates and so on. So that's what you would expect. Obviously, production, you'd have proper certificates. So Zipkin is the tracing engine that lets us see a request. Now, this is really important in microservices because in a microservice environment, a request can potentially go through lots and lots of microservices. It's not like you can just attach a debugger to a Java enterprise application. So let's have a quick look at this request and see the steps it went through. This is a feature that is dependent on the framework. I am using Helidon here for my microservices, and Helidon has built-in support to generate the Zipkin tracing information. Different frameworks can do it. What you want is something that uses open tracing, which is the standard, which Zipkin, Jaeger, and several other tracing implementations provide. So you can see the request came into the storefront. We did a bit of security thinking, some initialization, and so on. Then we passed the request to the stock manager, which itself took a little bit of time because it's setting up a database connection. It made a request, little bit of toing and froing there, and then we got a response back. Now, of course, the second time we do it, all of that lazy initialization has already happened. So you can see the response came a lot quicker. And if we now go back to Zipkin and have another look, we'll see we've got another trace in here. And instead of coming in at 9 or so seconds, this came in at about 1/4 of a second. So again, if you have a look here, you can see these are much, much faster. Basically, the delay here, most of this time is making a request to the database. Okay. So that is how we get a service up and running and see what has been happening. Now, let's just do a quick recap here. What we have done is we have created a ingress controller. We have set up some ingress rules and some services which effectively map the incoming request to a service. The service is then attached or connected to a deployment. And that deployment contains replica sets and pods, and those pods are using configuration information. So the next question people say is, well, what happens if I change my configuration? Well, let's have a quick look at what happens if you change your configuration. Okay, so I am going to use the editor here to change it. It's built into the Kubernetes dashboard. It's just for ease of use here. There are obviously lots of options. So I'm going to change this and call it demo shop. Okay. And I'm going to update that. Now, if we go back to our pods on our storefront and we connect back into that, Oops. Okay, you can see that that change has happened pretty quickly, right? It's actually been reflected into the container almost instantly, within a few seconds. Now, the framework I am using checks for modifications to that configuration file, and it only does that once every couple of minutes. So if we go back in here and we have a look at our configuration, what we're going to do is we're going to make a request to another API endpoint, which is a status endpoint. Okay, and you can see that that change has now been made and it's now saying demo shop. Now, why would you care about this? For example, if you want to roll a certificate, you want to upgrade things and stuff, as long as your application looks for changes, you can do that. Right? Now, there are a lot of other things that Kubernetes does. We've only got about 5 minutes left in my part of the session, I believe. So first of all, I'm going to have a very quick look at the Q&A, and I know that my colleagues have been happily answering questions for us on here, just to see. Okay, so right, ingress controller. If you haven't seen this, do we recommend ingress controller? You can use the Nginx ingress controller. There is also one that is built into OCI itself. You can also use one of many other ingress controllers. It's really important to understand here that OCI and OKE, which is our Kubernetes environment, is a standard Kubernetes environment. That means that anything that's certified to run on standard Kubernetes will work, okay? So you can use whatever ingress controller you want. You can choose whichever one you want. I would say that the OCI native one has some benefits in that it's got better integration with things like the certificate management server that's built into OCI. However, there are also customers who want to focus more on the open source environment, and therefore they would prefer to use an open source version like Nginx. So the answer is it will depend on what you want. And that's what Mika said there. Right, can the private key be accessed by a user? So if you have the administrative rights, the answer is yes, it can. In the same way as if you're running as root, you can probably override the security and read the certificate file for a certificate that's running somewhere, okay? Kubernetes does have security controls that you can apply around that, and that's one of the reasons why we recommend using namespaces to handle all of that. Okay. Right. Certificate and OCI Oracle training. I know Violetta has answered that one. I don't know a lot about that, so I'm not the right person to answer OCI training. Okay. Now, I'm just going to talk a little bit about some of the stuff that's been happened here. And the reason I'm going to do this using slides is some of this stuff is really difficult to visualize physically, even with the dashboard. So first of all, let's talk about packing. We've got 3 workers in this cluster, and we've actually only got 3 microservice pods, but we could have got hundreds of workers and thousands of pods. A typical Kubernetes deployment, for example, one in the finance sector I happen to know, has over 1,500 different microservices, and there are generally between 10 and 100 instances of each of those microservices, though in some cases I know of one customer who's running over 1,000 instances of a microservice during typical banking hours. So this thing can scale a lot. And what you don't want is you don't want to have all of this on the same worker. What happens if a worker fails? There may be a power supply failure in the worker. Obviously, when we build the clouds, we do the best for availability, but you've got to allow for the fact that computers fail, software fails. So let's figure out, first of all, how we can protect against the failure at the worker level. Well, what Kubernetes does is it is designed to handle failures. When they looked at Kubernetes, they said, let's just accept that there are going to be failures and work out how to handle this. So I'm going to show you a simplified version. Imagine you've got hundreds, thousands of microservices and tens of thousands of pods running here, right? Now, just to be clear, I am not saying that this is Tetris, just for copyright reasons, but this is quite a nice example to show you how things fit together. If you have the T-shaped service and you've got 2 instances, Kubernetes will allocate them as best it can to different workers. Kubernetes is also going to try and balance the load across all of those workers. So if you then have another set of microservices coming along, let's say the square microservice, it doesn't put them both in worker B and C. It's again trying to balance it. Now, obviously, in this scenario, there's the same number of blocks for each of those microservices. In reality, each microservice would have different resource restrictions and also different resource desires, so these will be varied. Again, this is just easier for visual purposes. As we add more and more microservices, Kubernetes tries to maintain the workload across all of those workers for us automatically. And over time, the workers gradually fill up. Obviously, that's not necessarily a problem because some workers may go away. So if we then run out of workers, we've now obviously got a situation where we've got 4 instances, but only 3 workers. We have to work out where to put that last one. So Kubernetes will do the best it can, and it will put it on one of the workers. If we had 6, it would have 2 on each of the workers. Now, a couple of points to notice here. You've noticed there's some gaps. Like the game that this is not, things don't necessarily fit exactly. This is one reason why we try and balance the workload. And there are mechanisms in place to allow you to have workers of different shapes. Now, what happens when you get a request? We've seen how the request gets into the cluster using the API gateway and web application firewall and so on. But once it's in a cluster, it goes to the service, which is not just a DNS entry, but it's also a load balancer. And it can do various different types of load balancing. So a request gets shifted, in this case, between the squared services. That also applies to a request that is generated from within the cluster as well as external requests. It will by default do round robin, but you can do affinity if you want. Now, oops, I've already done the configuration change, sorry. So that's how we distribute requests. But what about availability? Now, we're going to see in a minute, if the worker fails, it will just restart the pods on different workers. What happens if the pod fails? Well, we can restart failed pods. We can restart hung pods. We can ignore pods that aren't ready to handle requests. Those last 2 do require the application to provide a bit of information saying I'm active or I'm hung. Actually, generally, if I'm hung, it means it doesn't respond to the request probe, but also I'm not ready to handle requests and so on. And we can also do rolling upgrades and rollbacks, as I mentioned before. So let's have a quick look at this. If a pod fails or a pod does not respond to the "Are you alive?" request, it gets killed off, and Kubernetes will automatically restart that pod for you as part of a replica set. Now, in this particular case, I'm showing it as being restarted in the same worker. It clearly doesn't have to be. It could have been restarted in worker A. It wouldn't have been allocated to worker C unless there was no space in the other 2 workers, because worker C already has a version of a pod running. If a pod is not ready, for example, it may be taking a long time to start up. And we do have some customers who run an entire WebLogic server inside a pod. This is obviously huge. So that's not an instant startup process. The worker can provide a response to say, I am not ready to process a request. It may be that the worker is dependent on something that is no longer available on a temporary manner. In that case, the request would be coming in, but if the worker is not ready, there's no point in sending a request to it because it's not going to be able to process it. So Kubernetes keeps track of that for us, and any requests will automatically get sent to only the workers that are reporting as ready. There's a lot of situations where you would use this. It's not just startup. There's a lot of dependency situations here. There's also some special support for how the startup process works. And if you remember the deployment, there was a section on liveness and readiness probes that effectively say to Kubernetes, this is how you check to see something that's alive. This is how you check to see something is ready to process requests. Lastly, I'm just going to talk about upgrades and scaling. So upgrades, Kubernetes supports a rolling upgrade process, and it does it while the system is online. So if we upgrade the L-shaped shape, then we are going to see that the first thing we do is we create a new pod that gets allocated. And again, Kubernetes knows that in this case, it wants to distribute the workload for that pod across the workers as much as possible, but also keep the worker load balance as much as possible. Now, in this case, when we created a new version of a pod, it will then destroy or potentially start sending requests to it, and then it will destroy one of the old ones. there is a set of balances that you can do to say how far above the working limit you want to go or how far below you want to go, so you can manage effectively the resources that are used here. In this case, I'm saying don't go below, you can go one above. Now, over time, obviously, we then do this process again, and we get more and more requests coming in. So over time, we are gradually migrating all of the old versions to the new version, but we are still processing requests throughout the entire process. The reverse happens if you do a rollback. Now, we looked here at a rolling upgrade. It also supports things like canary upgrades, where you can deploy a test system to see how well it behaves, and you can use things like a service mesh to send requests to that system for test process, but it's running in the rest of the environment. You can do things like recreating the whole service, so kill it off and restart it, blue-green deployments, and so on. Lastly, quickly talk about scaling. Kubernetes does automatic scaling. The load on a service can change over time. This can be driven by metrics, so for example, CPU, but you can also support it based on metrics that you provide yourself. We can do vertical scaling. Again, this is driven by metrics, but this does require a pod to restart if it needs extra memory and stuff like that. And we can also scale the whole cluster. So if you add extra capacity, that shouldn't say hung pods, my apologies. If you need to add extra capacity to the whole cluster, you can also have that done in an automated manner as well. When it scales down, you may find it will restart some pods, however. So horizontal scaling, you've got the square thing, it's running, it decides it needs a new instance, it creates a new instance and it deploys it. Notice here it's had to put it on worker A because worker B does not have any capacity of the right shape to fit that square one. Vertical scaling is if you've got a heavy load on a pod and it can't necessarily scale horizontally. And there are obviously some applications that do this. They're usually applications that aren't really microservices. They maintain their own state. But in that scenario, you can basically tell the pod you're going to be shut down, it saves its state, and then restart it with a greater amount of capacity. We don't recommend that you use state in a pod, but some people still do. Lastly, we've got scaling across the whole cluster. So if this is really heavily loaded and we decide we want 2 instances, well, we go and create our start creating the 2 instances. And again, because of the shape in worker B, we've had to have these 2 on A, 2 on C. But there's nowhere left where we can fit that block. What do? Kubernetes can be configured to say, I'm going to request a new worker. So it requests a new worker, and then it deploys that in the new worker. Now, at that, as I say, if you want to do the lab yourself, you absolutely can. There's the link and the QR code. And I'm now going to hand this back to Violetta and for the close and some information for you. Okay.
Thank you, Tim. All right.
Actually, sorry, Violetta, I just have a couple of very quick questions.
Sure,
config scripts. So, McFui, I'm not sure when you say config scripts if you mean YAML files or if you mean shell scripts. There isn't really a clear answer to either of those, I'm sorry. Right, Mohammed, tracing. Most frameworks for cloud native include a tracing library that will automatically inject some kind of hash header into the request as it transfers for the system. So that happens for you automatically. A service mesh like Istio can do point-to-point. I don't see why a service mesh couldn't follow a trace across because it wouldn't know which outbound request was connected to which inbound request. Lastly, JJ, you have a question regarding pipelines. You can use kubectl to extract the YAML file in something that can then be fed in. That is really bad practice, however. You should always make changes to the YAML file and then deploy it, because then you know exactly what is deployed. Making a change to your cluster and trying to reverse it into the configuration, that's an opportunity for things to get out of sync. So that is not something that is recommended. Okay, thank you all for those questions and for your time. Violetta, over to you, or back to you.
Team, for doing this cloud coaching session for us today.
Absolutely delighted.
Thank you all for joining us. We hope to see you again soon. Enjoy the rest of the day and take care. Bye-bye.